All right, so if I look here, all right, the first part, so factors of a polynomial, this just reiterates what we talked about in the Desmos activity. So essentially, if these are your roots or your zeros or your x-intercepts, however you want to put it, they're all synonymous to each other. You would write it as y equals a times x plus or minus whatever the roots are. And again, it's based off the sign. So if it was a negative root, it'd be plus. If it's a positive root, it'd be minus. All right. Now, the a right here represents the leading coefficient. Now, remember how I said earlier when we were doing dance moves that what we created was kind of an incomplete function? What we're going to learn how to do is figure out what that a value is so that it is a complete function now. All right. And I'll show you how to do that in just a second. So let's look at this first example. So they want a quadratic function whose roots are -3 and 4, which passes through the point to -50. And they want it in standard form. So first thing you do is you want the factored form first. Okay. Now, if I'm talking a quadratic function, when I convert it to standard form at the end, what would be the highest exponent for a quadratic function? Think of what a quadratic function is, what it looks like. What's typically the highest exponent in a quadratic? This is a quadratic function. What's the highest exponent? 2. Highest exponent of quadratic function is always 2, which means it has an x squared in there somewhere. All right. So we're dealing with a degree of 2. So if my roots are -3 and 4, we're going to start by doing what you guys are doing in your delta math, not your delta math, your Desmos, and writing out the roots as factors first. So I'm going to keep the a because I don't know what that is yet. What would be my first factor, Wyatt? Uh-huh. So for the -3, what would it be? X plus 3. And what would the second one be? X minus 4. Good. Take these, flip the signs. And by flip the signs, I mean add or subtract it to x. Now, before we start converting to standard form, we want to figure out what that a value is. Your a value, the help for the a value is going to come from this point. Now, what's so special about a point? If you're given a point, you technically have what two values? What makes up a point? X and y. So we now have an x value and a y value that coincide with each other. So how do you think I will solve for a with what I currently have using that point? I'll give you a hint. We did a lot of this back in Unit 1. Plug in. All right. So we're going to plug in. This is our x value. This is our y value. We're going to plug in the 2 for every x I see and the -50 in for the y. Then we're going to simplify, solve for a. So we're plugging in x and y, and then we're going to solve for a. That's what we're doing. So if I do that, I would get -50 is equal to a times 2 plus 3 times 2 minus 4. Now, PEMDAS states I have to do what first before I can even, touch moving things to the other side? I have to do some simplification first. So by PEMDAS, what do I need to do first? What's in the parentheses? So I need to do the addition and subtraction of these two parentheses. So I get -50 is equal to a times 2 plus 3 is 5 times 2 minus 4 is -2. Then what do I need to do? Multiply. Good. I need to multiply the 5 and the negative 2. So this will be negative 50 is equal to, and I'm going to write the negative 10 in front because it doesn't matter what order it's in. All right, because multiplication is commutative, meaning you can switch its places, same thing. Now, I now have a nice one-step equation. What's the only thing I got to do to solve for A? Divide by negative 10. So A would be equal to what? Positive 5. So I'm going to rewrite my function, including my A value. So my factored form of my function would be y is equal to 5 times x plus 3 times x minus 4. All right. Now, that's the factored form, but they wanted it in standard form. So they wanted it to look something like this up here. All right. They want to be like something x squared plus or minus something x plus or minus a constant. You did this a lot back in math too. What method, not distribute just yet, but you're on the right track, what method allows you to multiply those two factors together? FOIL or what's the other method? Box. So we're going to do a box method, and then we'll save the 5 to distribute at the end. All right. So I'm going to do a box method here. So that would be, I have an x plus 3 on top, x minus 4 over here. So my leftmost box, what will go there? So top left, what will go there? X times x, what is it? X squared. What about my top right box? What is it? It's 3x, because that's 3 times x. What about my bottom left? Negative 4x. And then bottom right, negative 12. Put the phones up. All right. Now, we are then going to pull it out of our function and combine the like terms. So remember, our like terms are right here. So I have y equals, and I'm going to bring out down the 5 because we still got to distribute it. But I now have x squared, and then what's 3x minus 4x? Negative x, and then minus 12. And my last step to make it a full standard form would be what? Distribute that 5. So I'm going to distribute to every term. So my standard form function would be y is equal to 5x squared minus 5x minus 12. So 5x squared minus 5x minus 12 after I distribute the 5. You guys have a weird look on your faces. What's wrong? It does distribute to the 12. I did that on purpose. Because a lot of times when I see y'all distribute stuff, you forget at least one term. It goes to everything. So it's not minus 12, it's minus what? 60. So guys, I make mistakes sometimes. That one was intentional. All right. I intentionally did that just to see if you catch it. All right. Sometimes it's unintentional. So if I ever have a mistake, call me out on it. All right. I'm not always right. I once said that 2 plus 2 is 5. So it's fine. So I get, my brain thinks faster than my hand writes. Or vice versa. So if I did a quick graph of it, first off, it's quadratic. So is it an even or odd degree? So would the degree be even or odd? What's the highest exponent, even or odd? It's even. So that means our tails are going to be facing in both directions. What direction would those tails be facing in? What's our leading coefficient? 5. Is it positive or negative? Positive. So both tails will be facing up. So I'm going to put my roots in, so -3 and 4, and I want both tails going the same direction, and it's facing up. So that's not exactly what the graph would look like, but it's pretty darn close. All right. Any questions on that? So it's literally putting together everything that we have already talked about today. All right. Now, look at exercise 2. So if we're given this equation, all right, we don't really know what the A value is. We don't really care. Yes. Yes. What is the x-intercepts here? So given that equation that I just highlighted, what would the x-intercepts or the roots be? Right, -2 and +5. Remember, if you set both of these equal to 0, solve for x. X is equal to -2, x is equal to +5. These are my two roots. So they would be here and here. Now, they want us to kind of show what each of these graphs would look like if we look at different A values. So this one has an A value of 1 because there's nothing in front of it. That's the unspoken value. This is 2. This is 4. Now, think back to Unit 1 when we talked about function transformations. This is a dilation, all right, meaning it gets either thinner or wider. If it's a value greater than 1, will it get thinner or wider? So think rubber band, guys. Vertical stretch or compression. This would be a vertical stretch. Does the graph get thinner or wider? Thinner. This is the original. Vertically, it gets thinner. So the bigger the number, the more thin it gets. So for 1, the graph would look something like this. All right. For 2, let's make that green. The graph will look something like this. It's slightly thinner than 1. And this ain't going to be a perfect drawing. We're just doing a brief sketch. It'll still have the same vertex, same roots and everything. It's just slightly thinner. And then 4 would be even thinner than 2. And again, this isn't like the perfect graph, but I'm trying. So just note that even though they have the same x-intercepts, because of what the A value is, it does change the way the graph looks. All right, it'll either make it wider or thinner depending on what that value is. All right, so here's what I want you guys to do. This is kind of your exit ticket for today. So in your groups, I want you guys to try exercise 3 on your own, work together in your group. I only want you to get to the factored form, including the A value. Now, if you want to take it a step further to do the standard form, that's fine. But for right now, I only care about the factored form. We'll go through the standard form tomorrow. But it's similar, not exactly the same, but similar to what we did in exercise 1. So they gave us our x-intercepts, but notice how there's 3. So that means how many factors will I have? 3. 3 roots, 3 factors. And it goes to the point 620. Now, after your group come to a consensus on an answer, I want one person from your group to write out your work on your group whiteboard. And the person that's going to do that is, if you're sitting at a desk and you have a red dot on it, you are now the transcriber. So you have a red dot on your desk, so y'all just rock, paper, scissors. All right. So that does not mean that that person's the only one that has to do the problem. You all need to be doing this problem. All right. But they just have to transcribe it on their boards before you leave today. You got a solid 10 minutes until class is over. It'll take you about 7 to do that. So get to work.